Okay, so I decided to make a little video for you to remind you of LeChatelier's principle as we get into our unit on equilibrium, which will go rapidly. So you'll remember that in equilibrium has several characteristics, but we say we have a dynamic equilibrium. It is not static. It is in constant motion. So if I just look at A forming B, well, in equilibrium we have our ugly double arrows. This double arrow means that this represents the forward reaction and the reverse reaction, but at equilibrium we have the rate of the forward reaction being equal to the rate of the reverse reaction. And so that is so important that you understand that it is the rate of the reaction. We're just finishing up studying kinetics. We've been talking about rate. And so when we get to the place where the rate of the forward reaction in reversible reactions, when the rate of the forward reaction equals the rate of the reverse reaction, then we are at equilibrium. If you were to observe this in a test tube, you would see absolutely no observable change. There would be no observable change. So you can't tell when it's at equilibrium, but we can tell when we put a stress on that system and cause it to get out of balance. So the rate of the forward reaction is equal to the rate of the reverse reaction. And one huge gigantic thing that you should hear over and over, the amount of A that I have is irrespective of the amount of B that I have. We are never, ever, ever saying that I've got equal amounts of A to B, equal amounts of A and B at equilibrium. We're never, ever, ever saying that. We're simply saying that this reaction goes in the same forward rate as it does in the reverse rate. So we need to own that business. Let's talk about how we can change that equilibrium, because a lot of what we do is predict. LeChatelier's principle says this allows us to predict what's going to happen when we change a system or we stress out a system that is in equilibrium. That means we apply some change. So you will remember this. So if you get it, go on. Maybe you don't. I'm just going to give you this little visual. I went to go find a video, so I didn't have to do one. I went to go find a video just to explain this to you very quickly. But they were all very riddled. Some were riddled with errors, and I just didn't like them. So you can find your own method of remembering these, but this is going to be, I'm going to show you visually, show you what, how I personally think about this. If I have a reactant A banging into reactant B, making product C and product D, okay? They are at equilibrium. That means the rate going this way is equal to the rate going this way. So they are at the same rate. So I would see no difference in the concentrations or any observable change. So the concentrations would remain the same. That means A would remain the same because it's going to be going this way and being formed, being used and being formed at the same rate. So I would see no change in the concentration of A. Now, what would happen to this system if I added another A? Well, if we think about this, just based on the kinetics, if we have more A around, don't we have, and A has to bang into B to make C and D, don't we have the probability of a higher probability of colliding with B to have an effective collision and make product? Yes, we do, just simply by the reason that we have more A around. And so now if that happened, what would happen to the amount of B that you had? Well, it would go down because you've got more A's around. They are outnumbering the B's. So the B would go down a little bit. But now how I like to think about this is, so what that says in essence is this reaction, if we add A, we are going to shift the reaction to the right. So the reaction is going to shift right. So I can think about this very quickly. This is just sort of my visual. If I get a question that makes me think twice. I like to think about it this way, which is different than the way everybody else thinks about it. You can find your own way. But if I think about it as in I have taken the amount of a reactant, anything on the reactant side, and I pushed it up. I increased it. So I am increasing this rate. I have shifted my seesaw, and now everything, so my reaction has to go this way. You know, if you lift up the side of a seesaw, your reaction shifts this way. That's how I think about it. Almost everybody else in the whole world probably thinks about it different. Other people say if you add more this way, then what do you have to do? You have to push it this way. I don't know. They do it a different way. But I like to think about it this way, as in if I increase, now this means I am increasing, that's what my up arrow means, is increasing. And so everything's going to fall to the right. The opposite is also true. If I were to increase, let's set it back straight. So if I were to then add more of this, so if I increased this side, that literally means I'm pushing it up. In my mind, that's how I think about it. I'm pushing up on the reactant side. I'm lifting it up because I'm increasing, and therefore everything is going to slide to the left. Okay, so that may make sense to you. That may make no sense whatsoever. I will tell you how other people think about it. You can pick your own. But when I talk about it, this is what I am talking about. Just so you're not confused in case you see it somewhere else. But however you want to visualize it is completely a personal choice. Or you don't have to visualize it at all. But it's very helpful if you do. A lot of people say that if you increase A, that means you're like, so we add A, all right? That means we are adding weight, like adding a person to a seesaw. So you're pushing down on it, and then if you push down on it, what is the system going to do to fix it back? Well, it's going to add on to this side and to push it back down. It's going to add the C or the D to push it back down. So either way you like to think about it is great. I just wanted you to know where I am coming from, because I guess I never even really thought about it that much until I went to go see what these people were talking about, and I just was like, what? And so anyway, that is my take on it, and it works for me, and you just find whatever works for you. But when I think about increasing, I think about I have increased this side. If I increase anything on this side, well, I don't know what I'm doing now. If I increase anything on this side, I have shoved this thing up, and so everything's fallen this way. Now, we could do that. We could talk about that with concentrations. So something we can do that's like increasing the concentration. The same is true if we begin to, let's say I have 2 of these, or let's say we have more than that. which one's duplicate? This one. Okay, so let's say we have more of these. And our system is running and we are at equilibrium, and then all of a sudden I start pulling these off. Well, as this goes away, what am I doing to my system? Well, in my mind, this is where we're reducing this amount, so it's going down. So that means that the pressure on the lever is down, and everything's going to fall this way. So my reaction goes forward. Okay, so another way to really think about this is your reaction is trying to replace the yellows that you are removing. That's what the reaction is trying to do. It's trying to get back to equilibrium where it had more yellow here. And so this is how industry drives reactions without having to use extreme temperatures and that kind of thing. Particularly if you have a gas, or you take then you funnel your gas off. You have a gas escape, especially if it's only one product. If you only have one gaseous product. So you funnel your gas off. Well, that keeps your reaction driving to make sure, in the forward direction, to make sure that you are efficiently using all of your reactant, and it's more economical. So the other thing that we can think about is, like I said, you're not going to always be asked. You're not going to be just asked what happens because of one thing. You're going to be asked what's going to happen to the amount of, like I said a while ago, what's going to happen to the amount of the B. So if this is A, and this is B, and this is C, and here's D and D, well, the questions are more typically for AP, what happens if you have a vessel and you're making a gas, okay, and there's a leak in the gas vessel, and this gas is escaping. What happens to the amount of C? That becomes your question. Well, the amount of C is going to go up because you are removing this product. When you're removing the product, you're driving the reaction this way. They might also say, what's going to happen to the concentration of B? Well, B is going to go down, okay? So, and so would A. All right, now, so those are the sorts of questions. They'll say, something happened to A, increase, decrease, whatever. Something happened to A. Well, what happens to B, C, and D? Those are become your questions. So that's sort of the mindset we need to be thinking about. So we can change concentration. We can change pressure. Now with pressure, it's not, we have to think about our reactants as in a box. And I don't know, maybe not, but. So we have this equilibrium, and this is for gases, okay? Now this only works, we only talk about pressure when we're talking about gases, of course. But let's say we take this, and this, and this. And in this size container, we have 3 moles of gas. Okay, I'm going to call that 3 moles of gas. So 3 moles gas in our reactants. And then in our products, we have 2 moles gas. So we'll take a red and a yellow. All right, so 2 moles gas. Now, we manipulate pressure and equilibrium. This is in equilibrium, so I need those double arrows. Thank you very much. Since we are at equilibrium, our forward rate is equal to our reverse rate. And we are going to remember that we are going to manipulate pressure. What is pressure? Just think about it. How hard are they banging into the sides of the container? It is the force on the container. The pressure with which this thing hits the container is the pressure. That's the force. Pressure is a force. So that's the force that we're measuring, okay? Now, how do we make it hit the side of the container harder? Well, we can't get in there and push it and make it hit it harder. We could give it some heat energy, right? Make it, we're increasing their kinetic energy, and so that would make them speed up. That means they're moving faster, which means they're going to hit the sides more often, increasing the collisions with the sides of the container and with each other. And so think about that one for your kinetics test. And then, so how are we going to manipulate this pressure? Well, the only way we truly manipulate pressure other than temperature is, I don't know what I did, volume. So, and some of y'all tried to write about this, but it just came out all sideways. So be careful as you're thinking about this. So pressure, increasing pressure, we're going to decrease the volume. That's the way we're going to do it. So if we cut the volume in half, the volume of our container in half, well, not in half, we're just going to reduce it. Just pretend that's half. Now we've squished up these things, right? They're closer in contact with each other, and so the collisions are going to be more frequent simply because the space in which they are moving around is reduced, which increases their opportunity for collisions, which increases their opportunity for effective collisions. Okay, so now, okay, so I've said these are your reactants and these are your products. But in reality, though, let's think about this. Aren't they in the same vessel? Because gases, these two gases are going to form products, but they're going to be in the same vessel. So really and truly, we have to think about putting this all together. So here we have no separation. They're not separated. They are together. So there's no separation. Okay, so now let's think about it like this. Okay, so now we've reduced the volume, and if we reduce the volume, we've increased the pressure, right? Well, that also means that you're going to send your reaction. So if you increase the pressure, it was at equilibrium. Now the system's going to try to get back to equilibrium. And the only way it can get back to equilibrium is to have the pressure return to what it once was. Well, what's the easiest way to do it? It's either going to, it's got two choices. It can make more reactants or it can make more products. So what is it going to do? It's going to make more products. So you're going to shift the reaction toward the fewer moles of gas so that you are returning the gaseous system to equilibrium. That's what it's going to do in order to return to equilibrium, the pressure equilibrium. Because in a gaseous system, we just have to think about it, it's not the same as having a concentration. Those are gaseous particles bouncing around, and they are going to try to return to that nice and easy pressure that they had before. So they're going to produce, the reaction will shift in the direction that produces fewer gas moles in order to return to equilibrium. Okay, so if we decrease the volume, then we are increasing the pressure. That's our shift, would be increasing the pressure. So we're going to shift the equilibrium. Okay, now here's a tricky kind of question. I'm just going to give it to you now. There is a, well, that's not going to work. So if sometimes they'll say, I need to make another one of those. Sometimes they'll say, we have the system that's at equilibrium. Let's go back to our equilibrium. So we have a system that is at equilibrium. Okay. This is one of their faves, so know this one. A system at equilibrium. This system, these are still our reactants and our products, and we're going to insert an inert gas. So we're going to put in, that's an inert gas. What is going to happen to the reaction if we put in an inert gas? Inert means it's not going to react with anything in here. It's just going to bounce around. We can add those all day long. But due to the nature of gases, we are not going to change our equilibrium. Our equilibrium is going to remain the same, because these are going to be everywhere. So if you insert a gas, then an inert gas, these gases ignore each other. Remember, they're going to ignore each other unless they're going to react. And so putting an inert gas into a gaseous system at equilibrium has zero effect. Has zero effect on the equilibrium itself. Does it increase the overall pressure of the container? Yeah, but that pressure is an individual thing. So the pressure of one gas is not affecting the pressure of another gas. That's individual measurements. So adding an inert gas has no effect on the equilibrium position of a gaseous system. I'm writing in a place that you can't even see. Oh my goodness. I'm sorry. That's an inert gas. And inert gases have no effect on the equilibrium position. What does position mean? We always talk about that. It's like a place, but it's not a place. It's a state in the reaction where the forward and reverse reactions happen at the same rate. It is where these reactants get in like resonance with, don't say that word on the AP test, with the products. And so they're forming and reforming at the same rate. So we call it a position. Now, so I went and redrew this because I could not make it draw a straight line. I can't draw a straight line. Okay, so we started this whole unit talking about how if this is reactant A and this is product B or P, at the beginning of the reaction, we have a lot of product A, and this is like the reaction progress, or as time goes by. And so we have a lot of reactant A, and as time goes by, the amount decreases and then levels off. At the beginning, we have no product, like it's on the 0 line. So this is your measure of concentration. So this would be concentration. And so you have no product, and as time goes by, it increases, and then it finds a place where it levels off. Unit here this semester, looking at spontaneity and looking at whether or not the reaction was favorable. And so what is that? Delta G is the only thing that can tell favored reactions. Okay, so if it is thermodynamically favored, that means what's delta G? Delta G favors exothermic reactions, right? So that makes a negative delta G, not necessarily that it's exothermic. It also has to do with, so that's delta H being negative, but it also has to do with and that's the disorder, and favors more disorder or an increase in delta. So the combination of these two things determines whether or not it is altogether favorable. Is it gonna go? without adding energy. And then, so that was our thermo. We figured out how to figure out delta G. And then in this place, isn't this time as time goes by? So now, then we just finished looking at rate, the rate at which reactions happen, and that was our study of kinetics. So remember writing rate law and rate expressions. Okay, so then we come to the place where, well, that's not supposed to be there. We come to the place where they start leveling out. Oh no. And at this point, this is what we call equilibrium, where the concentration of A maintains, the concentration of B maintains, and the rate of the forward is equal to the rate of the reverse reaction. And this, my friends, is equilibrium. That's an equilibrium. Equilibrium. So that's where we are now, okay? So equilibrium. When the forward and the reverse reactions occur. So a lot of what we do in this unit is look at these places. And are we there yet? Are we there yet? Are we at equilibrium? So far we've looked at LeChatelier's principle, and we talked about if we stress by increasing or decreasing a concentration, that the system tries to use up an increased concentration by shifting either in the forward or the reverse direction, or it's going to try to replace it if you take it away. Take away something, it's going to try to replace it by shifting in that particular direction. And then if we have a system of gases, then it's going to respond by pressure. So if you change the pressure, by increasing the pressure, we're going to shift to the side with fewer moles of gas. And if we decrease the pressure, we're going to shift to the side that has more moles of gas. So moles of gas is inverse to the change in pressure. So we just have to literally count the number of moles of gas that we have on each side of our equation. And so the other thing that we can change is temperature. So if we look at changing temperature, I have an example for you, but I want you to think about changing temperature. I'm just fixing to clear this ugly board. And so we're going to clear everything off and start over. Okay, so if I have this reaction and it's making this, okay? Now, if this reaction happens to be endothermic, I'm adding heat. Yep, that's heat. I'm adding heat. So, I said exothermic. If it's endothermic, right? Endothermic, if you're taking in energy. So, this is the reaction. If I increase the heat, what's going to happen to this reaction? Well, logically, we know that if it takes heat energy to make these things collide at all, then adding heat energy is going to increase the opportunity for collisions, the frequency of the collisions, therefore the frequency of, or the possibility of more frequent effective collisions. So adding heat energy is going to drive the reaction this way, to the right. On an endothermic reaction, you drive the reaction to the right. So you could think about it just exactly like it's a reactant. What happens if we add more A? If we add more A, then we're going to shift it to the right. Well, just pretend that it is the same thing, and you're going to shift it this way. Okay? It's trying to use up that extra heat energy to get back to its place of equilibrium. And so For an endothermic reaction, and this accounts for every endothermic reaction, when you increase the temperature on an endothermic reaction, you drive it forward. The drive is forward. You're going to shift forward. The same is true if you have an exothermic reaction. Let's erase this so nobody thinks this comes in and sees that. So over here, if we have an exothermic reaction, and we add heat, we already have heat. If we add heat here, what's going to happen? Not this. We're going to drive the reaction in the reverse order. Something else that you need to really understand is that just exactly what I just did. Did you notice? Okay, so we are at equilibrium. This is the same exact reaction. If it is endothermic in the forward reaction, what does it have to be in the reverse reaction? Yep, it has to be exothermic in the reverse reaction. This is very key. This is not always intuitive, but you need to make it that way. So if you are endothermic in the forward reaction, that very same reaction in the reverse is exothermic, okay? So you just need to think about that way. You're going to shift it. Just pretend that your heat for an exothermic is a product. You're increasing a product. You're going to shift it away from the product side. Okay, so whatever side you're increasing something of, you're going to shift it the opposite way. Hey, that kind of looks like Mickey Mouse. Yeah, never mind. Okay, so I have one last thing to show you. Okay, so we have two gases. Or we have this reaction, and the reaction is the formation and decomposition of dinitrogen tetraoxide. So this is nitrogen dioxide. So two of these in equilibrium. And so this particular gas is brown. So the NO2 is brown colored, and the N2O4 is colorless. So I've sort of represented those to give you an idea. Okay, so if we look at the delta H, we should know whether this is an endothermic or an exothermic reaction, right? What's it going to be, a reactant or a product? So then we took these very same two flasks and we put one in a container with ice. Okay, so these are identical. They both started off as a mixture in equilibrium, and now one is being chilled. So I want you to predict what is going to happen. So you should be able to predict you should see a color change, and you should be able to predict what that color change is going to be. So is it going to get darker, or is it going to get lighter? And you should be able to use LeChatelier's principle to explain that. Please make your posts to me on Edmodo, not to the class. It's points. And then see about your other assignment, your little lab. Toodles.